Beyoncé is driving along a straight highway at t equals 0 when she is moving at 10 meters per second in the positive x direction. She passes a signpost at x equal to 50 meters, and her x acceleration as a function of time is given below. We are supposed to do a number of things, starting off with sketching the graphs of acceleration, velocity, and position, all as functions of time. What I'd like to do is begin by marking the acceleration here. Acceleration should have meters per second squared as the units. The time will be here in units of seconds. And what I'll do is I'll work my way from the bottom to the top. The idea here is that the acceleration is related to the velocity in this way. For over short periods of time, the acceleration can be thought of as the change in velocity divided by the change in time. In other words, it's the slope of the velocity versus time graph. Likewise, the velocity for short enough periods of time can be thought of as the change in position divided by the change in time. In other words, that is the slope of x versus t. And so what we'll do is we'll start with acceleration down below and work up to velocity and so on. What we notice is that the acceleration given by this function is a linear function of time. It starts off with an intercept of 2 meters per second squared. And then it goes down linearly with a slope of minus 0.10 meters per second. So if we were to mark on this graph, let's call this 1, we'll call this 2 meters per second squared. This will be minus 1 and minus 2 meters per second squared. We know that the graph should begin at 2 meters per second squared and go down linearly. It goes down linearly in such a way that it'll pass through 0 at a particular time. The acceleration is equal to 0. You can solve for the time at which that happens. It happens at t is equal to 20 seconds. So what I'll do is I'll mark approximately 20 seconds here. And if that's 20, then this is roughly 40 seconds here. And therefore, I know where the graph should go to 0. And if it goes to 0 at 20 seconds, it actually comes out to be minus 2 meters per second squared at 40 seconds. And so I can sketch the graph. It's a straight line that goes through 20, goes through 0 at 20 seconds, and goes to minus 2 at 40 meters per second. Now, the next thing we want to do is sketch what the velocity looks like as a function of time. Velocity has units of meters per second. The time is indicated here. And let's again mark the special time of 20 seconds, and we'll mark 40 seconds here. Where do we even begin? We know that the velocity starts at 10 meters per second. And so if I were to mark that on this curve, I would mark, let's say this is 10 meters per second, this would be 20, and this would be 30. I know that the graph is going to start at 10. And then what should happen? Well, since we know that acceleration tells us about the slope of the velocity graph, notice that that means that according to this graph here, slope of velocity versus time is greater than 0. But notice it starts off with a large number and gets smaller and smaller and smaller. That tells me that this graph should start off with a positive slope. It'll continue to go up, but its slope will get less and less steep. So it'll do this kind of thing as it goes through to 20. At 20, the slope should be 0. In other words, that curve should be flat. Let's try this to make it a little bit better, something like this. And then afterward, it'll start to come down because at this point, the slope is negative. And so this will be negative slope, negative slope, negative slope. So the curve should look something like that. Okay, once we have acceleration and velocity, we can now figure out what the position is going to look like as a function of time. Here's x in units of meters. On this horizontal axis, we've got time in seconds. Let's again mark the special time of 20 seconds. And we can mark 40 seconds as well. We're told that at t equals 0, the position is 50 meters. Let's put that down over here, 50 meters. What we know is that the slope of x versus t, that's what the velocity graph tells us. Slope of x versus t is always greater than 0. So this curve that I'm about to sketch is always going to be increasing. However, notice that the biggest slope should happen at 20 seconds. So this curve starts off going up, slope is increasing. At 20 seconds, the slope should have the steepest value, and then the curve will continue to go on with a positive slope, but getting less positive, and less positive. So it has this rough kind of shape. You can imagine sketching this out with a computer and doing even better. Let's try just a little better. Something like that. Okay, in part B, using calculus, we can find the x velocity and the position as functions of time. So let's go ahead and do that. We have to remember what the connection is between acceleration and velocity. We have to remember that the derivative of the velocity with respect to time is the acceleration, and that tells us how to figure out what the velocity is. The velocity would therefore be the integral of the acceleration, which is itself a function of time. We're doing that integral with respect to time, and we're going to do this with an indefinite integral, leaving us a integration constant in the mix. So what does this look like? The function we're to integrate is this, 2.0 meters per second squared minus 0.10 meters per second cubed t, and we need to integrate that dt. When you do that integration, this term is constant, giving you a linear term. This term has a t in it, so this is 0.010 meters per second cubed, t squared over 2. And then there needs to be an integration constant. That's what we might call v naught. And now we can use additional information. We're told that v naught is 10 meters per second. 10 meters per second. And so when I clean this up, the velocity as a function of time can be written as this 10 meters per second plus 2.0 meters per second squared minus 0.05 meters per second cubed t squared. That would be our answer. Can we get the position as a function of time? That can be done. It's the similar idea, realizing that the derivative of position with respect to time is what gave us velocity. And the idea is, therefore, we can determine the position as a function of time if we integrate the velocity, which is a function of time, dt. We'd have to stick inside this integral, the expression that we just found, 10 meters per second plus 2 meters per second squared t minus 0.05 meters per second cubed t squared. Integrate that dt. When we do that integration and we include our integration constant, I'll just write down here the integration constant we'll have is x naught, which we're told is 50 meters. What we'll discover, I'll let you fill in the gaps here, is that x of t turns out to be equal to 50 meters plus 10 meters per second times t plus 1 meter per second squared times t squared minus, and there's a rounding that has to be done here, 0.017 meters per second cubed times t cubed. Importantly, notice that this does not take on the form that the typical kinematic equations take. Yes, there is this term, the linear term in t and the quadratic term in t, but because the acceleration depends on time, there is this additional term to worry about. Lastly, when is Vx the greatest and what is its value? As a reminder, we determined that Vx was given by 10 meters per second plus 2 meters per second squared times t minus 0.05 meters per second cubed times t squared. The idea here is that when v is the greatest, That occurs, I'll just write here, greatest or maximum, occurs when the derivative of Vx with respect to time is equal to 0. That's an extremum. Now notice that dv dx, dvx dt, I should say, that derivative, that is just the statement about the acceleration. It's when is the acceleration equal to 0. So we can do the calculus here, but you would just realize that dv dx would be the derivative of all of this, which would give you back the acceleration function, which is given here. I'll let you do that as an exercise. When is that equal to 0? That occurs at t is equal to 20 seconds. So that is the time at which this happens. And then what is the value? That's the last thing to do here. V of x at 20 seconds is equal to 10 meters per second plus 2.0 meters per second squared times 20 seconds minus 0.05 meters per second cubed times 20 seconds quantity squared. And when you work that out, you'll find that this is 30 meters per second, which is approximately what I had shown on the graph before. Let's go back to it. This really should be at 30 meters per second.